All right, welcome back. And this time we are going to briefly cover how we are going to improve the previous estimate. And now we're going to estimate this area using 3 rectangles. And then we'll follow by learning some new words and how we can apply these words to this situation to make this notion of estimating areas a little bit nicer. So, all right, so we want to do kind of the same 4 cases that we had before, where we're doing a left endpoint approximation, a right endpoint approximation, an upper approximation, and a lower approximation. In order to split this up into 3, we want to split up this interval here into 3 different rectangles this time. So we need an x1 and an x2, and it looks like x1 should go about here, and x2 should probably go about here. Cool. So to set up our left endpoint approximation, we simply want to think about each of these rectangles. What is the y value of the left endpoint? So here, my left endpoint of this rectangle between x0 and x1 is going to be x0. So I want to trace over the y value here up until I get to x1. And I'm going to bring it down, and I have a rectangle. For the next rectangle, which lives between x1 and x2 this time, I want to, again, find the y value of the left endpoint. The y value is, the left endpoint here is x1, and the y value on the graph is a little bit lower than the previous y value. So we want to trace that over until we get to x2. And again, we'll have some area here. And let's see, now again we want to think about the rectangle that lives between x2 and x3. And so I'm going to find the y value corresponding to the left endpoint of this subinterval. So that's the y value associated with x2, which lives all the way up here. And we want to draw that rectangle as well. And I suppose I'm going to use, I suppose we can use black to shade this. Cool. So now if we want to set up the formula describing the actual area here, we would have something like A equals, and if we set this up so that our rectangles all have base equal to the same length, they all have, they're all of equal width here at the bottom, then what we've done is we've taken this interval of length b minus a, and we've split it into 3 pieces. So each base is going to have length b minus a over 3. And for the left endpoint approximation, here I'm multiplying by f of x0 for the height of the green rectangle. To that we need to add, for the red rectangle, again we'll have base length b minus a over 3. The height of the red rectangle was determined by the y value over x1, so that's f of x1. And last, we want to do plus, for the black rectangle, its base is also going to be b minus a over 3, and its y value was determined by the y value of the left endpoint, which is f of x2 in this case. Great, so we have a left endpoint approximation here. If we wanted to do something similar with a right endpoint approximation, we would have the same notation set up here, x2 and x3. Except for the y values of each of these rectangles, I want to use the right endpoint. So here at x1, or here for this first rectangle, I want to grab the y value at x1. So this is a slightly shorter rectangle than we used for the left endpoint approximation. For the rectangle between x1 and x2, I want to use the y value living over x2. And for the rectangle living between x2 and x3, I want to use the y value at x3. Cool. So again, if we want to come up with a formula for area here, the green rectangle has base, again, b minus a over 3. It has y value, f of x1, because we used x1 as the point at which we determined the height of the rectangle. The red rectangle is going to have base b minus a over 3 as well. And it's going to have height f of x2, because we used x2 to determine its height. Then last, the black rectangle will also have base length b minus a over 3, and we used x3 for the height there. So notice the difference between the two formulas here that we have. We have one formula for our left endpoint, one formula for our right endpoint approximation. And one of them, the only difference between the two is the indices, or the subscripts that we're using on the x's here. Notice that our left endpoint approximation uses the subscripts 0, 1, and 2, whereas the right endpoint approximation uses the subscript 1, 2, and 3. Otherwise, the formulas are identical, but it does produce differing results, as you can see by the fact that this green rectangle is very different from this green rectangle, this red rectangle is different from this red rectangle, and the same with the two black rectangles. Great, so we have our left endpoint approximation and our right endpoint approximation. We also want to talk about our upper and lower approximations. So the notation here gets a little bit messy, but that is the way of things when we are doing some of these approximations. So let's see, so we'll have an x0 still, we'll have our x1, we'll have our x2, and we'll have our x3. We want to first focus on about this interval here. And in order to do the upper approximation, we want to find the largest y value, which for us looks like it's occurring right at this left endpoint here. So I'm going to draw that rectangle. And we've been using stars to denote the x values which maximize the function. And so we're going to call this left endpoint here x1 upper star, meaning that it's the x value which maximizes f in the first rectangle. Great, so we want to move on to the second rectangle, and now we want to think about x values between these 2 points, x1 and x2, and it certainly looks like the largest x value on that or the largest y value on that interval is going to occur at the right endpoint. So here we are going to use x2 to determine the height of this rectangle. And so we're going to color this rectangle. And we're going to call the x value, which maximizes f in the second interval, this is going to be x2 star. Last, we have this interval here, and the y value, or the maximum y value here, occurs right around this peak. And so we want to use that peak as the height of our rectangle. And let's see, so then we want to shade in this rectangle. And we want to call the y value, which maximizes this or the x value, which maximizes f on this interval, x3 star. So if we want a formula for our area here, we can we want to add up the areas of the green, red, and black rectangles. As before, these are supposed to be equally spaced, so that all of these 3 rectangles have the same base length. And for the green rectangle, that again will be b minus a over 3, and its height was f of x1 star. For the red rectangle, we have again base length b minus a over 3. Height of that rectangle was f of x2 star. We want to use the x value, which maximizes f. Last, we have, for the black rectangle, we have a base length b minus a over 3, and height of that rectangle is going to be f of x3 star. All right, and again, we see we have some upper estimate here for what the area exactly is. but our upper estimates keep kind of getting better as we increase the number of rectangles. All right, last up we have our lower estimate. So we have a and b and x0, x1, x2, and x3. We want to find the smallest y value on this first interval here. So that occurs at the valley, and we want to create our rectangle based on that y value. In the middle interval here, we want to think about where the smallest y value is, and it looks like that occurs at this left endpoint here. Oh, we should have given the x value a name in the previous step. So that x value looks to me, we're going to call that x1 lower star to indicate that we're minimizing f. On the second interval, we have that our smallest y value occurs at the left endpoint, actually. So we're going to be able to use that as the height of our rectangle. And this area, we'll do the area calculation later. Finally, for this last subinterval here, we want to use the smallest y value, which occurs at the right endpoint, it appears. And so we're going to draw in that rectangle as well. Oops. Great. All right, so we want to think about our area formulas now, and let's see. So area is going to be the area of the green rectangle, which still has base b minus a over 3. It has height, f of x1 lower star. To that, we want to add the height, or the area of the red rectangle. We should have given our x values which minimize f names, so we'll call this one x2 lower star, and in the third rectangle we'll call that x3 lower star. So to get the area of the red rectangle, we'll have b minus a over 3, f of x3 lower star, and to get the area of the black rectangle, we will have base b minus a over 3, and f of x3 lower star. Oops, I made a mistake earlier. This x3 lower star should be an x2 lower star because we're in the second interval here. All right, so let's kind of call your attention to the differences between these two formulas. Here, the only difference is actually the location of the star. In the upper estimate, we're calling our x values upper star. In the lower estimate, we're calling our x values lower star. Note that they are defined differently, however. The upper stars are defined to maximize f, whereas the lower stars are defined to minimize f. So the x values that we're using are actually very different numbers here. Okay, so we've been talking sort of vaguely about this notion, but maybe we have a better idea of exactly what's going on here as we're doing these approximations. And we want to give ourselves some words to talk about these different concepts here. So we've got some definitions. So we're going to start with letting a and b be an R. So if you haven't seen this notation before, this means a and b are real numbers. Ooh. Sorry about that. Come on. A and b are real numbers. It's just a shorter way of writing it. So we don't have to write let a and b be real numbers every single time. With a less than b, so a and b here are exactly the thing you think that they were based on our previous work. Then what we're going to do is we're going to say that a partition of the interval ab is a set of numbers x0 through xn, with a equal to x0, less than x1, less than x2, less than x3, less than ... less than xn equal to b. So we want these numbers to be increasing, and we want the smallest one to be equal to a, the largest one to be equal to b. So this is what a partition is. It's just some set of numbers with this particular property here. The intervals from xi to xi plus 1 are going to be called subintervals. of AB, and if all of the subintervals have the same length, the partition is said to be regular. So we have the words that we are defining here are the words partition and the words regular. Those are going to be kind of the key things to know, and what we want to do is we want to be able to check when do we have partitions and when are our partitions regular. So let's think about this example 11 here. We've got a equals 2, b equals 5, and we have three numbers here. X0 is 2, x1 is 3, and x2 is 5. And we're asking the question, do they form a partition of the interval 2, 5? What are the subintervals, and is it a regular partition? So we want to maybe think about this somewhat geometrically, despite the fact that we've defined it very algebraically. And if I were to draw a number line here, and we've got 2, we've got 5, and we also have 3, we know that A is 2 and B is 5, and we're told that x0 is 2, x1 is 3, and x2 is 5. So the thing that we want to check here is it the case that A equals x0? And we look on our number line, and yes, it certainly is. Is it the case that x0, that all of the x's are increasing as their indices are increasing? And I say, well, yes, x0 is less than x1, x1 is less than x2, so we have that this part of the statement is true. And the last thing we need to check is xn equal to b? In this case, n is 2, since that is the largest index that we're given. And in fact, x2 is equal to b. So we can conclude, yes, this is a partition. We're not done yet. We are asked this next question of what are the subintervals. So let's see. Ooh, I forgot to mention we are also defining this word subinterval here. So let's see. So our subintervals, we're told, are these intervals xi plus 1. So this means this means that the intervals that we're considering here are the ones whose indices are adjacent. So things like x1, x2, x2, x3, x0, x1, x5, x6, things like that. So if we want to list out the subintervals, we'll have x0, x1, we'll have x1, x2, and we'll have x1, x3. So x0, x1 is the interval 2, 3. x1, x2 is the interval 3, 5. Oh, and we don't have an x3, do we? Cool. Never mind about this subinterval. Great. So we have our two subintervals listed here. The last question that we want to answer is this a regular partition? And we're told that the partition is regular if all of the subintervals have the same length. So we want to think, well, what exactly is the length of these subintervals? And let's see, length of this subinterval is going to be equal to 1 because the difference between 3 and 2 is 1. Whereas this subinterval is going to have length equal to 2 because the difference between 3 and 5 is 2. So these do not have the same length. Our two subintervals have different lengths, so this partition is not regular. All right, I think we've answered all the questions. We've decided that they do form a partition because the smallest one is the left endpoint, the largest one is the right endpoint, and they're listed in increasing order, so x1 is between x0 and x2. We've decided that we have two subintervals here, from 2 to 3 and from 3 to 5, and we have decided that they have different lengths, so the partition isn't regular. The way that maybe we would make this partition be regular is instead of having 3bx1, we would move x1 over about half a unit so that each of our intervals, or each of our subintervals, would have length 1.5. So if x1 were 3.5, this would be regular. All right, let's do one more of these. Let's see. So for a equals -6, b equals -5, do the following four numbers form a partition? What are the subintervals? Is it a regular partition? So again, I want to think maybe about drawing a picture here. Important to remember that -6 is less than -5, so -6 lives to the left while -5 lives to the right. We've said that -6 is A, -5 is B. And we want to look at these numbers. X0 is -6, x1 is -5.75, x2 is -5.5, and x3 is -5.25. Cool, so let's see. So first we want to ask, do we have a partition? And we check, is A equal to x0? Yes, it is. Is B equal to x4? Yes, it is. Let's see, what other things do we need to check? Is x0 less than x1? Yep. x1 less than x2? Yes. x2 less than x3? Also yes. And x3 less than x4? Also yes. Since we have all yeses, this forms a partition. Great. What else are we asked? We want to find what are the subintervals. So our subintervals, we know have the form where we have like x0, what's that? X0, x1, and we have something like x1, x2, and x2, x3, let's see, x0, x1, x1, x2, x2, x3, and x3, x4. Great, so these are the intervals from -6 to -5.75, from -5.75 to -5.5, from -5.5 to -5.25, and from -5.25 all the way to -5. All right, so we've listed our subintervals, and now we want to think about, we want to think about their lengths in order to check whether or not this is a regular partition. And we notice that the length for each of them is going to be -1/4, or not -1/4. Each one has length +1/4. I'm going from -6 to -5.75, and that's 0.25 units long. Likewise for the second subinterval and the third subinterval and the fourth subinterval. And since these numbers are all the same, we can conclude that this partition is regular. So notice that this idea here is kind of what we were going for earlier when we were breaking down the interval a to b into those rectangles. We wanted to split it up so that these rectangles were equal to, all had the same length, and that's exactly what we mean by a regular partition. So we're just giving ourselves a little bit more vocabulary here in order to talk about these different subintervals and to be able to later define what it actually means to be the area under the axis. All right, I think that's enough words for the moment. We'll get a couple more of them in the next video.